In this lecture, we are going to expand on what we learned in the previous lecture on mean variance optimization. In the previous lecture, we looked at how to set up the mean variance optimization problem, and we talked about how you would go about solving it in code. This lecture is meant to take a more big picture perspective. What do we actually get when we solve this problem, and how can we use the results? Let's recall what the quadratic program we derived earlier actually gives us. It says that, given a specific target return, and given some particular constraints on the weights, tell me how I can allocate my portfolio so that I can achieve the smallest possible variance. Let's see what that means in terms of the risk-return plot. Earlier, we drew a risk-return plot showing random portfolios. We saw that these points seem to fill out a pretty well-defined curve called the Markowitz bullet. Let's consider the question, what does mean variance optimization have to do with this curve? We can begin by considering how we might apply mean variance optimization. First, recall that we know how to find the minimum and maximum possible return given a set of assets. For that, we can use linear programming. So let's say we've done that and we found the min return and the max return. Now, let's suppose we take small steps from the minimum to the maximum, say 50 or 100 steps. So for example, we might start at -2% and then go up to -1.9%, -1.8%, and so on. For each of these possible returns, we will consider them the target return. Then, for each of these target returns, we will find the minimum variance portfolio for that return. This will give us the best possible risk level for each of these returns. Basically, you should understand that by doing this, we will draw an outline of this curve. Why do we get an outline? Well, consider any point inside the curve. We know that these points cannot possibly be optimal, since all we have to do is move to the left to achieve less risk. Solving the quadratic program we derived earlier will automatically give us the leftmost point corresponding to the minimum risk for the given return. The top part of the curve we have just drawn has a name. It is called the efficient frontier. Any portfolio along the efficient frontier is called efficient. Why are they efficient? Because for each of these portfolios, if you take the expected return that they have, there is no better portfolio that will give you less risk. Conversely, you can look at it from the risk first. You can say, for each of these portfolios, at a given level of risk, you can find no better expected return. Thus, these portfolios are efficient. Now you might ask, why don't we consider the bottom part of this curve? These portfolios are not efficient because all we have to do is go up, and we found a portfolio with the same risk, but with higher return. For the rest of this lecture, I want to discuss a few alternative ways that you can find the efficient frontier using constrained optimization. Let's start with a simple one. What if we want to get rid of the bottom half of the curve, the part that is not part of the efficient frontier? In this case, it's simple to reformulate our quadratic program. All we need to do is replace the equality constraint on the target return with an inequality. We say that mu transpose W must be greater than or equal to the target return, rather than just equal. In this way, the quadratic program is allowed to minimize the risk with any larger return. You can imagine that this will push the solution upwards to the point where we have minimum variance. Previously, we looked at the scenario where you want to start with the target return and optimize the weights such that they minimize risk. But what if we wanted to look at this the other way? What if we want to start with the target risk and then figure out how to maximize the return? As a portfolio manager, you can imagine how this would be highly practical. A client may come to you and say, I don't want more than 5% risk. What is the highest return you can give me? Well, we can do that as well. In this case, we want to maximize mu transpose W with respect to W. This corresponds to the portfolio return. This is subject to the constraint that the portfolio variance is less than or equal to the target variance. As usual, we have our constraint that the weights must sum to 1 and other optional constraints on the weights. Note that this is not a quadratic program because we have a quadratic constraint. A quadratic program has quadratic objective and linear constraints. However, this problem is convex. If you want to learn more about these kinds of problems, I would recommend learning about convex optimization. Yet another formulation of the problem is this. Let's suppose that we want to be able to tune the risk relative to the return. Our objective is now the portfolio return minus some hyperparameter tau multiplied by the variance of the portfolio. We want to maximize this objective. If you have a machine learning background, this should remind you of the concept of regularization. We are essentially penalizing the expected return by adding a cost for the amount of variance that the portfolio incurs. Tau is called the risk aversion parameter, and of course this allows you to specify how important the variance is relative to the return. Of course, tau must be positive so that your penalty is positive. As usual, the weights must sum to 1, and you can have additional constraints on the weights. Note that because the objective is quadratic and the constraints are linear, this is another instance of a quadratic program. Okay, so to summarize this lecture, here's what we've done. First, we defined the efficient frontier, and we discussed what it means to be efficient. Next, we looked at alternative ways of finding the efficient frontier. The first way was to use the quadratic program we formulated in the previous lecture. This is to minimize variance given a target return. The second way was to do the opposite. We can maximize return given a target variance. The third way was to introduce a risk aversion parameter where we maximize the return penalized by the variance.